And then I'm going to get ready for reviewing some material in case depending how much time I have. All right, let's go here. I'm wondering if anybody ever studied Latin. If you did, maybe you know what Locus Somniorum means. It's the name of my internet connection. It's actually a feature on the moon. Let's see, let me enlarge this a little bit here. Yeah, so I've got a certain amount of material I want to review. So let me get started on that. The perturbation theory involves a lot of formulas and stuff, and some of it is difficult to motivate. But let me just try to go over and explain where we ended up and what the notation is. So we got a Hamiltonian has an unperturbed part in the perturbation. We want to solve H psi equals E psi. So E and psi are the exact eigenvalues and eigenstates. The unperturbed eigenstates are denoted K alpha with an energy is epsilon sub K, and the alpha resolves degeneracies. That's just the notation for that. We introduce an operator P, which is a projector onto the unperturbed eigenstate N. That's the one whose perturbation we're interested in. And I also introduced another operator called R, which is short for resolvent. It's got energy denominators. In fact, it's the reciprocal of E minus H naught, however restricted to the space that's orthogonal to the nth unperturbed energy eigenspace. Turns out that's a useful operator in this whole scheme. Anyway, after some machinations, you end up with a basic series that expresses the exact energy eigenfunction as a power series like this carried out to infinity, where you've got a bunch of operators acting on P psi. P psi is a projection of the exact eigenstate onto the unperturbed eigenspace, and therefore P psi is an unperturbed eigenvector itself. In any case, this applies in all cases, degenerate, non-degenerate, nearly degenerate, all the different cases of perturbation theory you might want to look at. In the non-degenerate case, the N alpha gets replaced by N because there's no degeneracy in that level of whose perturbations we're interested in. And that means that when you project psi onto it, you get something that's proportional to N. And we choose the normalization in phase of psi to make that C equals to 1 so that P psi is equal to N. So if you do that, then all these P psis that occur here, there, and there, and there, and these terms can all be replaced by N. And then if you take that series and you multiply by H1 and N on the other side, rearrange a little bit, you get a series for the energy. This is again is a non-degenerate case. G, this is your basic formula for the energy in non-degenerate perturbation theory. There's the zeroth order term, of course, is the unperturbed energy. The first correction is the expectation value of the perturbing Hamiltonian with respect to the unperturbed eigenstate. And the second one is a similar expectation value, but it's got H1 with a copy of R in the middle. That's the same resolvent operator as above. And if you write it out explicitly, it turns into a sum like this. You can see that this R operator is a resolution identity excluding the K equals N states with an energy denominator. And that's just what you see here is you got this K alpha outer product and the energy denominator. That's the R operator that was right there. Anyway, this gives you the usual result for non-degenerate perturbation theory for first order and second order corrections, which you've probably seen in your undergraduate course. There's also the correction to the wave function psi. This is really this version of this series up here where P psi has been replaced by N. The first term is N. And then the second term here with P psi again replaced by N turns into that. That's just RH1 acting on it. But in any case, this is also a useful formula for first order non-degenerate perturbation theory. It gives you the correction in the wave function. And you can see the correction is orthogonal to the original unperturbed eigenstate. That's because this K sum excludes the case N. So these K alpha states here are all orthogonal to N. Basically, if you think about it in terms of if you think about it in terms of a vector, it's the unperturbed eigenstate. The perturbation moves it perpendicular, in Hilbert space to where it was. At least to lowest order it does. At higher order, there's corrections that are also parallel to it, but that's the idea. All right, so that covers a non-degenerate perturbation theory, and I launched into degenerate perturbation theory at the end of the hour last time, but I think it went by pretty fast, so I'm going to go over it again more quickly. But the basic thing to do is to go back to the basic series here and just reanalyze it in the case where you got degenerate perturbation theory. So allow me now to do that. The P psi is the projection of the exact eigenstate onto the unperturbed eigenspace. And therefore, this has to be a sum of the unperturbed eigenvectors in that eigenspace, which I'll write as n beta times coefficient, so I write as c beta. So in this general series, I want to take the P psi that appears there and there and there and all these different places and replace it by this sum. So if we do, what we get is then that psi is equal to, there's an operator acting on this, and the operator is 1 plus lambda RH1 plus lambda squared RH1 squared, RH1 plus dot, dot, dot. And then that acts on this n beta like this, coefficient c sub beta, and I'll take the sum and put it out the front here, like so. We get an equation like that. Now then, next I allow this equation, I let it act on the left-hand side by E minus H0, and on the right-hand side, I allow it to be acted on by lambda RH1. And in fact, these two operators are equal to one another. So on the left-hand side, I get E minus H0 acting on psi. And on the right-hand side, I get the sum on beta. And then I get, let's see, yeah, I get lambda, see, am I doing this right? E minus H0, I'm sorry, E minus H0 is not lambda RH1, it's just lambda H1, that's all it is. That's just rearranging the original Hamiltonian. So I get lambda H1 here from that first term, and then I get lambda squared H1 RH1. And then the next term would be lambda cubed H1 RH1 RH1. You can see the pattern there. And then I got the n beta, and then I've got the c beta like that, okay? Now, having done that, let me sandwich the left-hand side by n alpha, an unperturbed state here, and n alpha on this side as well. N alpha, I hope you can see that there, and it's not too cramped. As far as the left-hand side goes, E minus H0 acts to the left on the n alpha. The E is a C number, so it just comes out. The H0 acts on n alpha and brings out the unperturbed energy epsilon n. So this thing turns into the quantity E minus epsilon n times the scalar product of n alpha psi. Now, I didn't say this up here, but if I take n alpha and sandwich it on both sides of this equation, what I get is n alpha P psi just picks out the alpha coefficient on the right-hand side, which is C alpha. But the P acts on n alpha and doesn't do anything to it because it's a projector onto the unperturbed eigenspace. So the left-hand side is the same thing as n alpha psi. So these scalar products n alpha psi are the same thing as C alpha. And so this left-hand side can be written as E minus epsilon n times C alpha. And on the right-hand side, bringing this n alpha in here, what I get is a sum on beta. And I get n alpha on the left. I get this operator, lambda 1 plus lambda squared H1 RH1 plus dot, 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 like this, n beta, and then C beta like this. And if you look at the structure of this, this is turning into this is in fact the basic equation that you use to analyze degenerate perturbation theory. The E minus En here is the energy shifts, the shifts in the energy away from the unperturbed eigenvalue, which is epsilon n. The C alpha and C beta here plays a role of an eigenvector. By the way, this sum on beta that you see here runs from 1 up to what I'll call G, where G is the order of the degeneracy, the order of degeneracy. That is to say, it's a number of linearly independent eigenvectors in the eigenspace n, like this. It might in some cases just be 2, in other cases it could be infinity, it could be, there's a lot of possibilities. but in any case, it's the order of the degeneracy. So this matrix that you see here with N alpha on the left and N beta on the right is a G by G matrix. And it's indexed, as you can see on the left and the right, by the unperturbed eigenvectors that lie inside the unperturbed energy, degenerate energy eigenspace, which is multidimensional under the assumption we're making. Now, in most practical applications, we can ignore the lambda squared and higher order terms there. At least that gives us the lowest approximation. So let's do that for starters and just ignore them. Let me also set lambda equals 1 because it's distracting to do otherwise. And if we do that, then what we get is an equation that looks like, I'll also rewrite it, I'll also swap the two sides, and we'll write it like this. It becomes a sum on beta of N alpha scalar product with H1 in the middle, N beta like this, times C beta is equal to E minus epsilon N times C alpha. And this is the most useful, in practice, the most useful, it's the lowest order result, and it's in practice the most useful result from degenerate perturbation theory. What this tells us is that the energy shifts at first order in degenerate perturbation theory are the eigenvalues of the matrix, which consists of the matrix elements of the perturbing Hamiltonian inside the degenerate eigenspace of the unperturbed system. Here you see the N is fixed on both sides, but the alpha and beta are variable. To make it explicit, B goes from 1 up to G here, the order of the degeneracy. So this is a G by G matrix here. The C's are the eigenvectors of that matrix. And the eigenvectors appear up here because they give you the expansion of P psi in terms of the unperturbed eigenstates. So if you know the eigenvectors, then you know what P psi is. You know what the projection of the eigenvector, the exact eigenstate is onto the unperturbed eigenspace. In fact, that's the 0th order part of the eigenvector, the unknown eigenvector that you want. That's the part that's parallel to the unperturbed eigenspace. So that's determined by diagonalizing this matrix. If you want to know higher order corrections, including the part of psi that's orthogonal to the unperturbed eigenspace, then you need to go to higher order and take into account these lambda squared terms that are here. But normally that's enough to do it, just to do it this way. In other words, you get the unperturbed you get the perturbed eigenstate only to 0th order, but you'll get the eigenvalues correct to first order if you do this process. All right, so that's the case of degeneration theory. Is it normally is applied in practice. I'd now like to say something about what I like to call nearly degenerate perturbation theory. To do that, let me get some papers out of the way and center this. So for nearly degenerate perturbation theory, the motivation is this, is if I have my unperturbed system H naught and I plot the energy levels on it, something that happens an awful lot in practice is that you get energy levels that are close together. They form multiplets or near multiplets of nearly degenerate energy levels. This is common in practice because we oftentimes have systems in which have an approximate symmetry, which is broken by small effects. And these small symmetry breaking effects cause small splittings. For example, the case of the neutron and the proton, they have almost exactly the same mass. One is 938 point something MeV and the other one's 939 point something. The difference is like half an MeV out of 1,000. So it's like 0.0005 is the percentage difference. So there's lots of examples in physics in which we've got nearly degenerate states, and there's usually some symmetry argument behind it as to why that's so. Anyway, let's call one of these epsilon sub n and the other one epsilon sub m. Now, when we turn on the perturbation, it's very possible if the splitting is small, that the effect of the perturbation might completely overwhelm the splitting between these two states and to give you levels that where it's just run roughshod over the nearby nearly degenerate state. Now, in the construction of this R operator, this resolvent operator, we excluded from the sum the terms that were involved with epsilon sub n because we wanted to avoid small denominators. In a problem like this, we're going to get small denominators also from the nearby level epsilon m. And so you might think that one strategy to handle this would be to exclude both the m and n terms from the resolvent operator and then reanalyze things. And in fact, that works if you want to do it that way. But I'm going to propose a different procedure, which I think is easier, at least for the problems we do in this course. It works like this. Let's choose an energy value I'll call epsilon bar, which is somewhere near epsilon, these two nearly degenerate energy levels. It could be equal to one or the other. It could be the average. The point is it's not very far away from, let's just call it epsilon bar. And let's take the Hamiltonian for the system and let's rearrange it. And I'll show you how we're going to do that. So the original Hamiltonian, H is equal to H0 plus H1. And the H0, let me write it this way, is the sum on K and alpha of K alpha outer product times epsilon sub K. And to that we add the H1. That's the perturbation. Now what I want to do is to take this sum, which runs over all values of K and alpha, and split it up into two parts. The values of K and alpha that are not equal to epsilon, M, and N, the nearly degenerate states, and the ones that are. So let's do it this way. Let's write this as a sum on K not equal to N and M and alpha of K alpha outer product, epsilon K. And then let's write this as plus the sum of the correction term, which is K is equal to N and M and alpha of K alpha. Except what I'm going to do is I'm going to put an epsilon bar in here, and instead of an epsilon K alpha. And now what I'm going to do is correct this, because epsilon bar is not the true energy levels that need to go in there to make the H0. Now I'm going to put in another correction, which is this. K is equal to N and M, sum over the nearly degenerate levels, alpha like this. And now what we'll put in is outer product K alpha. And then let's put in epsilon sub K minus epsilon bar, like so. And then we include H1, like so. And let's call this first term, let's call it H1 prime, and let's call the second term H2 prime. So we have H0 plus H1 is equal to H0 prime plus H1 prime. Okay, same Hamiltonian now. We haven't changed the Hamiltonian, we just rearranged the terms. But look what's happened with H1 prime. H1 prime is the same as, I'm sorry, I should have called this H0 prime and this one H1 prime. H0 prime. H0 prime is the same as H0, except for the fact in the K in the N and M terms, when K is equal to N and M, the exact eigenvalues epsilon sub K, epsilon N and epsilon sub M have been replaced by epsilon bar, which is, as I say, is just a single value. And we haven't changed the eigenfunction, we've only changed the eigenvalues. The projectors are still the same. All right, so we changed the spectrum, but not the wave functions. This term corrects for it, but epsilon K minus epsilon bar is small. That's how it was set up here. In fact, it's really a first order is what it is. So it really should be taken as the same order as H1. So now what we do is we do perturbation theory on H0 prime and H1 prime. Notice that in the case of H0 prime, we can use degenerate perturbation theory, which I just described, because we force these two levels to come together and make a degeneracy. And then the difference that moves away from the degeneracy is now thrown in as a perturbation, and that's what we analyze by perturbation theory. So I'll call this nearly degenerate perturbation theory, which is useful in quite a few applications.
So just a question.
Yes.
You briefly mentioned that the epsilon bar and or in H1 prime, the two terms are like of a similar order of magnitude. So does that mean that the perturbation is a similar order of magnitude as the near degeneracy?
I mean, well, yeah, it's a similar magnitude as near degeneracy, because that's what this is. Epsilon K minus epsilon bars, you know. I mean, if I chose epsilon K to be the average between the two, this is like 1/2 the difference between them.
So is that basically what defines the extent of what near degeneracy is defined as?
Well, we need to worry about near degeneracy if the effect of the perturbation is enough to override it, overwhelm it, and that depends on H1. So we wouldn't be doing this if H1 weren't strong enough to ride roughshod over this energy difference and go way over it. I mean, it's possible H1 could be much bigger than this, you see. But what this strategy does is it reduces near degenerate perturbation theory to degenerate perturbation theory. So you know how to do it. That's the reason for it. There's other ways of handling this problem, more sophisticated, but this works. Okay. And we'll see in practice. There's quite a few examples of that. All right, then that's a perturbation, that's degenerate and near degenerate perturbation theory. And I'd now like to turn to some applications of perturbation theory, starting with the Stark effect. The Stark effect concerns the behavior of atoms in an external electric field. We're going to only deal with single electron atoms, which means either hydrogen or hydrogen-like atoms, or alkalis, in which we use the model of the screen nucleus, which I talked about in an earlier lecture. So I hope you remember the physical model and how it works. In any case, that's what I'm going to mean by single electron atoms. Let's look at the perturbation. First of all, we put the atom in an external electric field, which I'm going to note by F rather than E, because I don't want to confuse the electric field with the energy. So F is the electric field here today. In fact, we'll put F in the Z direction like this, F is Z hat. And so the perturbation V here is equal to the charge on the electron, which is minus Z times the potential. And the potential is the same thing as minus F times Z hat. So we get minus E F Z. Excuse me, there's two minuses make a plus. The scalar potential phi, see, this is equal to minus the gradient of the scalar potential phi. So the scalar potential phi is equal to minus, see, what is it? It's minus Z times F. So multiplying this minus Z times F, so multiplying by minus C, I get plus EFZ. So this is the perturbing potential V here. And let me call it V1 to indicate its perturbing potential. Okay, so that's what it looks like. The Hamiltonian, in the absence of the perturbation, is going to be a central force problem, kineticless potential, P squared over 2 plus V of R. The V of R in question, maybe I should call it V0 because that's the unperturbed potential. V0 of R depends on the case we're considering. In the case of hydrogen, of course, it's minus C squared over R. This is for hydrogen. In the case of the alkalis, it's just some potential V of R. I explained earlier the qualitative features of this V of R and what it looks like, you know, how it's a screen potential and so on, but there's no formula for it. So I'll just call it V of R in that case. In any case, that's the setup of the potentials. They're both central force problems, so the energy eigenfunctions are NLM in the usual set of central force quantum numbers in both cases. The energy levels in hydrogen depend only on the N quantum number, whereas in the alkalis, they depend on both N and L. And what that means is that there's a degeneracy, an order of degeneracy, which is different in the two cases, because in hydrogen, the energy depend only on N. In fact, we have a formula for En in hydrogen. En is equal to minus 1 over 2 N squared times E squared over A naught, which is the energy of the Bohr radius. So this gives an order of the degeneracy, which I'll put over here in another column. And that's equal to N squared for hydrogen. For the ENL for the alkalis, there's no formula for it. But perhaps you recall what the energy level diagram for atoms like sodium looks like, so you have an idea. In particular, energies are increasing function of L. This has only degeneracy of 2L plus 1 because that's the degeneracy in L is split in the alkalis, and it's only the M degeneracy that's left. So if I double underline the N here to indicate the quantum number that gives the energy level, it's N. Here it's got to be N and L is double underlined, and single underline the quantum numbers that give you the set of basis vectors inside the unperturbed eigenspace. It's Lm in this case in hydrogen, and it's just M in the case of the alkalis. All right, so that's the setup of the cases that we're going to consider here. All right. No, and this is an analysis of the unperturbed system and its degeneracies. Let's take a look next at the potential energies. Let's make some qualitative drawing of the potential energy. I'm going to do this on a new page to make space here. So, in fact, let's get this out of here. Let's just do one of these. So let's sketch the potentials. By the way, the potential for the hydrogen potential V of R is fully rotationally invariant. So it has SO3 symmetry, meaning full three-dimensional rotations. For the case of the alkalis, it's the potential is, well, this also applies to the alkalis, it's V of R. That's also SO3 because it's also a central force motion. This is the V zeros. But for the V1, which is the perturbation, that depends only on the coordinate Z. And so that doesn't have full rotational invariance. It only has SO2 invariance, which refers to rotations about the z-axis. So by introducing this external electric field, we've broken the full three-dimensional rotational invariance, and now it's replaced by just two-dimensional rotational invariance. That means that in the exact perturbed system, all that stuff we learned about, J multiplets and things like that goes out the window because it isn't rotationally invariant anymore. All right, in any case, that's some comments about the potential. So let's make some plots of the potential then. Let me draw a potential vertical axis here, horizontal axis. Let's plot this along the z-axis. We have various potentials we're going to plot. The unperturbed potential, whether it's Coulomb or whether it's a screened alkali potential, qualitatively it kind of looks like this. It goes to negative infinity as r goes to 0, and it dies off as r goes to infinity. Different functional forms, depending on whether it's hydrogen or the alkali, but that's what it looks like. The perturbing potential V1 of Z is equal to EFZ. We just worked that out. It's proportional to Z. And so that's a straight line on this diagram like this. This is the V1 equals EFZ, like so. If I add these two together to get the total potential, on the positive side, you see you have something that comes up like this and then goes up like that. And on the negative side, it follows the Coulomb potential at small radii, but then it gets influenced by the external field and it bends over like that and goes down out like that, going for negative Z. Okay, but the red line then is the total potential. Now, this system down here in this potential well, it's got some bound states, at least it does before you turn the perturbation on, like that. You can picture them like that. And one of the things you can see about this system without doing any work, just looking at the potential curves, is that when you turn on the perturbation with an external field, and in fact, it doesn't matter how weak it is, it doesn't have to be a strong field to make this happen. If you change the field strength F, what happens is this straight line wiggle, its slope changes up and down. But as long as F is non-zero, it's got a non-zero slope. And what that means is that this level, for example, has the ability to tunnel through this potential barrier here, like this, to come out here and then emerge into the real world and then produce a traveling wave that comes out like that, you see, going out to infinity. And the same thing is true for all these levels, as a matter of fact, but the deeper you go towards the ground state, the deeper the barrier is that they have to tunnel through. So this shows that when you turn on this perturbation, no matter how small it is, that all of the bound states of the original atom become unbound states. They become actually resonances or scattering states. Now, the lifetime of these states may be extremely long. It depends on the tunneling probabilities through this barrier. And the more shallow the slope is, the weaker the external field, the deeper the barrier is, and the slower the tunneling rate is going to be. In fact, tunneling rates depend exponentially, as we know from WKB theory, on the tunneling action. And so you can expect in some cases to have extremely long lifetimes, more than the age of the universe or something. You need to do the numbers depending, it depends on the state, you see, it depends on the state and the parameters of the problem. By the way, the atom has some levels that are piled up here near the continuum threshold, and those are actually above this red barrier. When you turn on the perturbation, those don't even begin to be bound. They become unbound states right away. They fly away, basically. This is what you call field ionization. The highly excited states are only weakly bound to the atom, and turning on the external field just rips them away. All right. Anyway, this is some qualitative features. A while ago, when I was talking about perturbation theory, someone was asking about the convergence of the perturbation series. We're going to be doing bound state perturbation theory in the Stark effect, and we're only going to do it to first or second order. But no matter how many orders you carry it to, a bound state perturbation theory is going to give you a bound state, at least nominally, that's what it's going to do. But as I just explained, these states are actually not bound. And bound state perturbation theory is never going to show you that tunneling. It will not appear at any order of perturbation theory. And the reason is that something goes beyond all orders. It's one of these functions that has no Taylor series expansion, like e to the -1 over x. except the x here should be replaced by the perturbation parameter. Anyway, this is a phenomenon which is very common in quantum perturbation theory. Typically, the series that you get are asymptotic and not convergent. All right, okay, so this is some qualitative features based on the potential energy. Now, let's talk about since we did the formalism perturbation theory, we did first order and second order perturbation theory. First order is of course easier. So let's try doing first order perturbation theory and for the Stark effect and see what we get to take the easiest things first. The first order perturbation theory in the Stark effect corresponds to what's called the linear Stark effect. And the reason, as I'll show you in a minute, is because it gives rise to an energy shift, which is linear in the applied field. There's also a quadratic Stark effect, which is quadratic in the applied field. We'll see that later on. But in any case, let's look at what we can do with first order perturbation theory. We had two versions of this. We had degenerate and non-degenerate perturbation theory, and the non-degenerate was simpler. So let's make our life simpler for ourselves. Let's take a case of non-degenerate perturbation theory first. So one way to do that is to look at the ground state of a hydrogen or alkali. In the case of hydrogen, the ground state has quantum numbers 1, 0, 0. These quantum numbers I write down are always the NLM central field quantum numbers that you have for any central force problem. But for hydrogen, the ground state quantum numbers are 1, 0, 0. If you took an alkali like sodium, the ground state is a 3, 0, 0. That is to say, the principal quantum number n is 3 for the ground state. The reason is in the case of sodium, the n equals 1 and n equals 2 shells are already filled. And so the valence electron has to start out in n equals 3. Be that as it may, for any alkali, the ground state has the form of n0, 0 for some value of n. So the energy shifts in first order perturbation theory for the ground state of hydrogen or alkalis then is just given by the expectation value of the perturbing Hamiltonian with respect to the unperturbed eigenstate. So it's just n0, 0 sandwiched around EFZ. Simple enough. The E and the F, of course, are constants that can be brought out of the matrix element, and the Z is an operator. Now, this matrix element vanishes, and the reason it does is by parity. The Z is odd under parity. Pi dagger Z, pi is equal to minus Z because it's a component of the position vector, which is odd under parity. Whereas the states n0, 0 on the two sides both have the same parity. I'll remind you that an NLM eigenstate of a central field Hamiltonian has a parity which is -1 to the L power. So since the L values are the same on both sides, the parity is the same on both sides. And you're trying to make the matrix element of an operator with odd parity. So the answer is going to be 0 unless the parity is different on the two sides. So by parity, we find that the energy shift in the ground state of hydrogen and the alkalis at first order is equal to 0, and there is no linear Stark effect. Now, at this point, I'd like to make a digression into a topic which is relevant for the linear Stark effect, but let me make the digression and then we'll come back to it. Let's talk about classical electrostatics, and let's define what we call the dipole moment of a charge distribution. I'll call it D here. I think in the E&M books they probably call it P, but that confuses it with momentum, so I'll call it D. And it's defined in classical electrostatics as the charge weighted position vector. If rho of x is the charge density, then you just integrate the charge density times x over all space and you get the dipole moment. In the case of a single electron, a single charge particle at a given point, this just turns into Q times. For a single particle, it turns into Q times x, where x is the position of the particle. Or if there's more than one particle, you sum on the particles with their charges Qi and their positions Xi. This is the dipole moment of a collection of charged particles. Distribution of charge density, you'd integrate over rho like that. Anyway, that's all classical. If you wanted to convert this into quantum mechanics, however, the most logical way to do it would be to take the charge density and classical charge density and replace it by the charge of the particle times the probability density of the wave function psi of x squared. And if we do that, the integral that I just wrote down turns into the following, turns the integral d cubed x, can be written this way anyway, if psi of x complex conjugated times qx in the middle, and then psi of x on the right-hand side. And that makes it clear that this is an expectation value. And instead of calling it the dipole moment of the quantum problem, we're going to call it the expectation value of the dipole moment operator, like this, with respect to the state psi, where the dipole moment operator is defined to be equal to qx for a single particle, such as we had. That's like the classical formula for a single particle. But now it becomes an operator in quantum mechanics, and this becomes the expectation value. So what was the dipole moment classically now becomes the expectation value of the dipole moment operator in the quantum problem. All right. Of course, in the case of an electron, where Q is equal to minus E, this turns into D is equal to minus EX, like so. All right. We'll be talking about electrons, of course, for our atom. All right. Now then, okay. Now, if a quantum state psi has a non-zero value of the expectation value of the dipole moment operator, then we say that it has a permanent electric dipole moment. That's just terminology, but that's how it's used. So on the other hand, what we saw for the ground state of hydrogen in the alkalis was that the first order Stark shift was 0, so there was no linear Stark effect. Well, the first order Stark shift, delta E at first order on some state psi, is just equal to psi sandwiched around the perturbation, which for our purposes was EFZ times psi like this. And this you can see is minus F, I'll write as F sub Z. F sub Z is the same thing as F because it's in the Z direction. The expectation value of minus EZ, psi like so. And so that becomes equal to minus F sub Z times the expectation value of the Z component of the dipole operator. And so this would generalize into a more general geometry into the dot product of the electric field dotted into the expectation value of the dipole operator. It would generalize in that manner. So what we see is that the vanishing of the linear Stark effect implies the vanishing of the permanent dipole moment. They go hand in hand, one implies the other. So the ground state of hydrogen in the alkalis has no permanent electric dipole moment, and therefore it also has no linear Stark effect. That's part of the moral that I'm drawing here. It's also an interesting fact that the energy shift in first order perturbation theory and the Stark effect, which I just wrote out here, is minus F dotted into D, expectation value of D. Well, in classical, to go back to the classical case, the energy of this dipole in an external field, call it delta E here, is given by minus the electric field F dotted into the dipole moment. You probably saw that written as minus P dot E or something, but I'm using different notation here, but that's the idea. And that's the energy of orientation of the electric dipole in the extra field. So if we had a quantum system, which did have a permanent electric dipole moment, then the linear Stark shift would be that energy of orientation of that permanent dipole in the external field. Okay, but we didn't find it, not in those two examples. All right. Now, this vanishing of the linear Stark effect and permanent electric dipole moment for the ground states of hydrogen and alkalis is not totally an idiosyncrasy of those systems, but it rather applies to a much more general class of problems. It's related to the fact that these systems, before we turn the perturbation on, they're isolated, and therefore they commute with parity. And also, it has to do with the fact that that the energy levels are non-degenerate. Let's put these two together. Let's suppose we have any system now, any system, which will assume when it's isolated, it's isolated before we turn on the external electric field, in an isolated system. And let's, for simplicity, let's talk about a non-degenerate energy eigenstate. Let's H psi equals E psi, and let's assume it's non-degenerate. That covers the two cases we had before, but a lot of others as well. Now, here's this theorem that keeps coming up again. The Hamiltonian here, by the way, commutes with parity. We know that because the system is isolated. In saying that, I'm neglecting the weak interactions, which normally one would want to do because they are extremely, extremely, extremely small. So let's do that. If we do so, then the Hamiltonian commutes with parity. Now, this theorem that keeps coming up is the following, is that if you have a non-degenerate eigenstate of one observable and it commutes with another one, then it's automatically an eigenstate of the other observable. What that means is the state pi is an eigenstate of parity. Psi acting on parity brings out some eigenvalue. We don't know whether it's plus or minus 1, but there's some eigenvalue that comes out. Our theorem I just quoted doesn't tell us the eigenvalue. Doesn't matter. The point is that under these circumstances, the non-degenerate energy eigenstate psi is going to be an eigenstate of definite parity, either even or odd. And therefore, when you sandwich around EFZ, you're going to get 0. So the vanishing of the electric dipole moment then came about. It actually applies to all systems, which are all systems which have non-degenerate energy eigenvalues. All systems, when they're isolated, have non-degenerate energy eigenvalues. All right. So, for example, it would apply to the grounds. It would apply to the alpha particle as an example of a nucleus, a spin 0. You see, there's many much more complicated systems we can immediately apply this to. All right, now, so what this means then is that if we're going to find a nonlinear Stark effect, we have to deal with degenerate levels. So let's take an example of that. Let's take the excited states of the alkalis or hydrogen atoms. So these are NLM like this. These are excited states, NLM. In the case of hydrogen, the energy levels, as I just explained, are En, and the degeneracy is N squared. For the alkalis, the states can be labeled the same way, but the energies are ENL, and they're 2L plus 1 fold degenerate. Let's take the case of the alkalis first because the degeneracy is smaller than it is in the case of hydrogen. So now what we need to do is degenerate perturbation theory. So let's remind ourselves, what do? You take the unperturbed Hamiltonian and you form its matrix elements inside the eigenspace of the unperturbed Hamiltonian. So the eigenspace of the unperturbed Hamiltonian for the alkalis is characterized by N and L. So I want to take these states NLM and sandwich around the perturbation, which is EFZ, and NLM like this on the other side. And the N and the L's, which I'll underline, we want them to be the same on both sides because they specify the unperturbed eigenspace. But the M values we allow to be different. So I'll put a prime on the M. See, they're not, these indices are not treated the same. And the result is we get a matrix, which is 2L plus 1 by 2L plus 1 dimension like this. And the energy shifts are going to be the eigenvalues of that matrix. That's the perturbation theory. Well, we don't need to run around diagonalizing big matrices to solve this problem. The reason is that this all the matrix elements for all values of M and N prime, they still vanish. And the reason is again parity. And the reason for that is that the parity of central force eigenstate NLM is given by -1 to the L, as to say it's independent of the magnetic quantum number. So therefore the parity is the same on both sides. And again, Z can only connect states of opposite parity. So the entire matrix is 0. And again, we get no linear Stark effect in the excited states of the alkalis. Okay. What about other excited states of other systems? You may recall this theorem that I quoted that this was back when analyzing the results of the Wigner-Eckhart theorem, that in isolated systems, the bound state energy levels consist of one or more irreducible subspaces under rotations. That means they have one or more J values, and each J value corresponds to a 2J plus 1 fold degenerate multiplet. And in fact, there's an addendum to that theorem that usually you only get one such eigenspace. The reason is it requires either a systematic symmetry or else a unlikely accident to make energy levels of different values of J coincide. And usually you just get a single irreducible subspace. That's what we had with the alkalis. You see, each of these NL specifies an irreducible subspace, and the M just runs from -L to +L. That just gives you the vectors in that subspace. But that's not just unique to the alkalis. That applies to what I'm just saying, almost all systems in the world. So what that means is that the linear Stark effect is going to vanish in almost all realistic systems for almost all realistic energy levels. Now, of course, near degeneracies occur, and we can do a more sophisticated analysis of how near is near, but how near does it have to be before it doesn't matter anymore. Let me not get off into that right now. I'll leave that as an exercise to think about. But in principle, these energy levels never have exactly the same, almost never have exactly the same energy eigenvalues, crossing different J values. There is one exception, however, and that's the case of hydrogen. Because in the excited states of hydrogen, there's a degeneracy. And this is only in the electrostatic model of hydrogen, by the way. It isn't real hydrogen. We'll get back to that later. But in the electrostatic model of hydrogen, there's an exact degeneracy among the different L values. And the different L values have different parities because the parity is -1 to the L. So we have a degeneracy amongst energy eigenstates of opposite parity, and that's what we need to get a nonlinear, to get a non-vanishing linear Stark effect. So let's turn our attention now to the excited states of hydrogen. Let's take the n equals 2 as the simplest one. The n equals 2 consists of two levels, the 2s and the 2p, which are degenerate in the electrostatic model. The 2s is a single level and the 2p is 3 levels for a grand total of 4 levels. So there's a fourfold degeneracy here. The 2 level has got quantum numbers 2, 0, 0, and the 2p has got quantum numbers 2, 1, m like this, where again, this is the NLM quantum numbers. The m here is equal to either 0 or plus or minus 1. That's how you get 3 levels there. Altogether, it's 4. So we need to do degenerate perturbation theory. We've got fourfold degeneracy, so we're going to have a fourfold matrix. So let's set up the matrix this way. Let's list the levels. Let's list them this way: 2, 0, 0, 2, 1, 0, 2, 1, 1, and 2, 1, minus 1. That'll be for the rows of our matrix. And for the columns of our matrix, we'll label in the same way. I'll just put down the quantum numbers: 2, 0, 0, 2, 1, 0, 2, 1, 1, and 2, 1, minus 1 for the rows and the columns of this matrix. So it's a 4 by 4 matrix, and it's going to have 16 entries. Let me divide it into 4 2 by 2 matrices. Now, what are the matrix elements we need to look at? We've got let's make it 2 LM on one side. Then we've got a perturbation EFZ in the middle. And then we've got 2 LM on the other side. The 2 specifies the degenerate energy level. And the L and the M give us the quantum numbers of the vectors inside that degenerate level. So we want to allow them to be different on the two sides. So I'll put primes on them over there on one side like that, but not primes in the 2. Well, the 2 is only one number anyway. Okay, so this is a matrix, which you see is a 4 by 4 matrix, which we're going to need to diagonalize to get the energy shifts. Now let's look at the selection rules of this matrix. First, we'll start with the Wigner-Eckhart theorem. The EF, of course, is a constant, so it can be taken out of the matrix element. The Z is the Z component of the position vector. Perhaps you recall that's the position vector is a k equals 1 irreducible tensor operator, and the q equals 0 component of it is just Z itself. In other words, this Z is the same thing as a T10 with a k equals 1 and q equals 0 operator. I'm sorry about the things getting in the way there. I hope you can see that. It's a T10 operator. So when we apply the Wigner-Eckhart theorem there's an L selection rule. It says that delta L can either be equal to 0 or plus or minus 1. That's because it's being combined with k equals 1. So this is the only new L's you can get from the old ones, they differ by 0 plus or minus 1. There's also a selection rule in magnetic quantum numbers. It would be m is equal to m prime plus q, but q is equal to 0. So we just have m equals m prime for that. All right. However, there's further selection rules from parity, coming from the fact that Z is odd under parity. And these two states, L and L prime, have parities -1 to the L and -1 to the L prime. This implies a matrix element vanishes unless delta L is odd. That's to say, you have to connect states of opposite parity because the operator Z has odd parity. Now, if delta L has to be odd, that excludes the delta L equals 0, which would have been allowed by the Wigner-Eckhart theorem. Now, this analysis I just went through of the selection rules coming from Wigner-Eckhart theorem really means proper rotations, and parity means improper rotations. So this is overall dealing with rotations, these selection rules. This analysis I just went through of these selection rules is exactly the same that you would do for the matrix elements governing electric dipole transitions between atomic states. And I talked about that before. They're the same selection rules because the matrix element is almost the same. For electric dipole transitions, we had the components of the position vector in the middle. And that's what we have here too. We got just the Z component, but still it's the position vector. The only difference is that in electric dipole transitions, the n values on the two sides would not be the same because you need an energy difference in order to get a transition. But otherwise, the analysis is the same. All right. Anyway, what this means is that many of these 16 matrix elements that are going to occur in here are zero. In particular, a delta L must be, the L values must be different. Let's take this one first. The L values must be different in order to get a non-zero matrix element. If they're the same, you get zero. So anything connecting 0 and 0 is give us a 0, and any of the 1, 1 connections will give us 0. So we have 9 matrix elements connecting the one to the 1 states, L equals 1 to L equals 1, and another one. So actually a total of 10 matrix elements are 0 already just from the delta L rule. Now what about the M equals M prime rule? So here's M equals 0. So it would not be allowed, it had a vanishing matrix element with M equals 1 or M equals minus 1. And then likewise down here, those two have to be 0 also. This matrix is Hermitian. If I do it on one side, the other side's Hermitian conjugate, so you can get zeros on opposite sides of the diagonal. This just leaves 2 slots, which are in fact are not forced to be 0 by the selection rules. Let me put an X in them like this. And so there's 2 matrix elements which are Hermitian conjugates of one another. This means that total of the 16 matrix elements, we really only need to evaluate 1 to do this problem. And that 1 matrix element is going to be 2, 0, 0 on the left. It's going to have our perturbation EFZ in the middle, and then 2, 1, 0 on the right. And I'll leave it to you to look up the hydrogen atom wave functions and to do the integrals of the YLMs with the EFZ. If you do that, what you find is the answer is minus 3F times A0, A0, which A0 is the Bohr radius. And let's call this minus 3W to define, in effect, an energy scale, which I'll call W, which is equal to 3EF times A0. Notice that what physically W is 3 times the amount of energy needed to move the electron from one side of the atom, that is to say a difference of the distance of the Bohr radius, in the external electric field. It's the energy of motion of that charge over the distance of the atom in the external field. All right, so that makes good sense as to what that is. So I made a minus sign here so that W would be a positive quantity because it's easier to work with. So these X's that I put in here are both minus W's. You can see this 4x4 matrix has got 2 eigenvalues which are 0 because of this lower block here. And then 2 others are going to come from this upper 2x2 block. So we only need to diagonalize a 2x2 matrix, which looks like this. This is the upper block here, written down explicitly. And this is trivial to do. If you find what you find is the energy shift center equal to plus and minus W. And in fact, so you get an energy eigenket plus W. Well, you get energy eigenkets for both plus and minus W here are the basis vectors that come out of this. Now the eigenvector of this matrix is, you'll recall in degenerate perturbation theories, a set of expansion coefficients giving us the perturbed eigenstate as a linear combination of the unperturbed eigenstate inside the degenerate space. So if I list these out, it works like this. For the plus W, the eigenvector is 1 over root 2 times 1 minus 1. And for the minus W energy, it's 1 over root 2 times 1, 1, 1 like this. Easy elementary calculation to work that out. So what this means is that the plus W energy eigenstate is 1 over root 2 times the linear combination, which is 2, 0, 0, minus 2, 1, 0. Whereas the state that's been suppressed in energy when you turn on the perturbation is 1 over root 2 times 2, 0, 0, plus 2, 1, 0. And I don't have diagrams of wave functions here, but you can work this out. It's easy enough to do. Take the hydrogen atom wave functions for the 2, 0, 0 and 2, 1, 0 state. And if you alternately add or subtract them, what happens is they interfere with each other and effectively move an electron, a blob of probability from either the positive z-axis down to the negative z-axis and vice versa as you go back and forth between them. Now you need to square that linear combination, some of those two wave functions, in order to get the charge density. But the net effect is the charge density is moved, a blob of it is moved up and down the z-axis in going from one to the other of these states. And that shows you why the energy is different, and also why the order of magnitude of the energy is an electron charge times the external field strength times the Bohr radius. That's got to be the order of magnitude of it. So this all makes good physical sense. All right. Let's construct an energy level diagram for this system. We started out with the n equals 2 levels, and there's 4 of them. And we see that when we turn on the perturbation, it splits like this. There's 2 levels whose energy doesn't change. So this is the H0 over here, and here's the H0 plus H1 energy levels. One of these has got an energy of plus W. I'll write that as the ket that corresponds to it. One's got an energy of minus W above and below the unperturbed level. And the other two, the ones that didn't change, if I go back to our table here, that was the 2, 1, 1 and the 2, 1, minus 1. So they're in the middle here, 2, 1, 1 and a 2, 1, minus 1, like so. So this is an energy level diagram for this perturbation problem. All right. Now, so I think I explained the basic physics of the plus and minus W states. What about the states that are 2, 1, 1, 2, 1, minus 1? They did not shift in energy. Why? Why is that? This is a nice example, by the way, of how a perturbations typically split degeneracies, but they don't always split them completely. Here's a 4-fold degeneracy, but after we're done, we have 3 levels. There still remains some degeneracy. This is only first order perturbation theory, and you might ask yourself, if we went to higher order in perturbation theory, would that remove this degeneracy of these 2 central levels? The answer is no, and you can see it by working through the exact symmetries of the problem. Let me address that question. Let's take the unperturbed Hamiltonian and then the Hamiltonian including the perturbation, and let's list the symmetries that it has. So H0, what symmetry is? I'll indicate symmetries by the operators that the Hamiltonian commutes with. So for the H0, it commutes with all 3 components of L because of the rotational invariance, it's angular momentum. It also commutes with parity because it's a central force problem. And it also commutes with time reversal because time reversal commutes with central force problems as well. When we turn the perturbation H1, however, as I mentioned earlier, the perturbing potential only has rotational symmetry about the z-axis, but not full rotational symmetry. So of the 3 angular momentum components, only LZ survives as a symmetry operator in the full system. What about parity? Well, we saw parity gets destroyed. Parity is violated by this. That's the whole point here. Is the perturbing Hamiltonian V1 is not invariant under parity. In fact, this is how you break parity. You put something in an external field, electric field. What about time reversal? Time reversal doesn't do anything to the position vector, and so it still commutes with that external potential, even though it's not a central force potential. So we still have time reversal invariance. Time reversal invariance applies for all electrostatic problems, including that quadrupole moment of the nucleus problem in your last homework. So we've lost part of rotational invariance, all of parity, and time reversal remains. So let's see what that implies for the full Hamiltonian H then. So H commutes with L sub Z. What does that mean? That means there are energy eigenstates that can be labeled by not only the energy, but also the quantum number of L sub z, which is M. It's a magnetic quantum number. There is no L quantum number anymore. H doesn't commute with L squared, which is the quantum number of L. L is the quantum number of operator L squared, but H doesn't commute with L squared. That's gone. And so the quantum number L is gone too. But the magnetic quantum number is still there. All right. What about parity is gone? What about time reversal? Well, theta H, theta dagger is equal to H. Hamiltonian commutes with time reversal. I'll remind you what that means is that if you have an energy eigenfunction and you apply time reversal to it, you'll get another energy eigenfunction of the same energy eigenvalue. That may or may not be degenerate with the first one, depending on whether the new function is linearly independent of the old one. Okay, but anyway, that's what it does. So time reversal applied. These, by the way, these are only approximate energy eigenstates of the total Hamiltonian, because we only did first order perturbation theory. But time reversal applied to the exact eigenstates of H0 plus H1 will map them into new exact eigenstates of H0 plus H1. Whether they're degenerate or not, linearly independent of the old one remains to be seen, but that's what it'll do. Now, what about angular momentum in time reversal? LZ theta theta LZ theta dagger. What is that? Well, it's the signal property of time reversal that it changes all angular momentum. It goes into minus LZ. And therefore, what time reversal will do is it won't change the energy of a state, but it'll change the LZ quantum number. It'll flip this into, what theta will do is it'll flip this into E and comma minus M. Now, is that linearly independent of the old one? The answer is this: if the magnetic quantum number is 0, then minus M is the same as M. And so all you've done is you've just said it's going to map a state of E and M equals 0 into another state of E and M equals 0. That could be linearly dependent on the old state, and therefore not a degenerate, not a new state. It doesn't prove a degeneracy, in other words. It might be, but it doesn't prove it. On the other hand, if M is non-zero, then the eigenstates with EM and E minus M are orthogonal to one another and are certainly linearly independent. And therefore, time reversal is mapping one into the other, changing the M value, but it doesn't change the energy. And therefore, you have two states which have the same energy, which are linearly independent. Therefore, there's a degeneracy. Well, look what we've got here. This is precisely the M not equals to 0 states, 1 minus 1, that are degenerate with one another. And what you can see from this analysis is that this is a degeneracy that exists to all orders, and it's because of time reversal symmetry combined with LZ. The combination does it. You see what theta will do is it'll flip one of these into change the M value, flip these back and forth. That's what theta does, but it doesn't change the energy. On the other hand, the W values, up and down, plus and minus W, they have only a fixed M value, which is 0. Time reversal doesn't say anything about a degeneracy when M equals 0. And in fact, these are non-degenerate. So time reversal maps the plus W state into itself and the minus W state into itself. All right.
So why doesn't H, the new H, commute with Lx and Ly?
Because the perturbation is in the Z direction, because it's look at the potential, it's EFZ.
Oh, right, okay.
The electric field's in the, it's in the Z direction, doesn't commute with it.
Okay.
It only commutes with LZ. I mean, just think about the system in the external electric field. It only now has rotational invariance about the Z axis. It's just physically clear from the electric field. Okay. All right. This analysis I just went through, by the way, is not Kramers degeneracy. That's another story. Kramers degeneracy is actually more important than this analysis I just went through. But this is an example of how symmetries play a role in understanding degeneracies. It's not Kramers degeneracy because, well, okay, it's a little tricky. Kramers degeneracy requires a half-integer spin. It occurs when you have half-integer spin. It says all energy levels are non-degenerate. And it would look like that's what we got here because we just got one electron. would have a half integer spin. Well, we do, except we've been ignoring the spin. So the analysis we're carrying out here is based on a spinless electron. And that's why Kramer's degeneracy doesn't apply. If we had included the spin degrees of freedom, then we would have Kramer's degeneracy, and you have to think about that. But you'd also have twice as many variables now because you got to spin and spin up and spin down. That's a different analysis. All right. In any case, that's the explains the remaining degeneracy. Now, okay, so enough of that. As I've been talking about this hour, the ground state of hydrogen in the alkalis has no linear Stark effect, and therefore no permanent electric dipole moment. The energy shift is zero at first order perturbation theory. What about second order perturbation theory? Is it possible there's a non-zero energy shift there? Let's look at that. Let's do it for hydrogen. Let's look at delta E at second order perturbation theory of the ground state. I'll write it like this. So if you just use the formula, this is now second order non-degenerate perturbation theory. So if you just use the formula, this is going to be a sum over all states in LM which are not equal to the ground state, which is 1, 0, 0. We wrote that earlier as K not equals to N, but this is what it is in this notation. And then what we've got is 1, 0, 0, the perturbation EFZ. Then we've got NLM. And then we've got NLM, the perturbation EFZ, 1, 0, 0. And this is divided by the energy denominator, which is E1 minus En, like so. All right, that's what that's equal to. Now then, no, I don't want to talk about this right now. I want to come back to this. Let me come back to this. I want to talk about something else. Here's what I want to talk about first. As I said, the linear Stark effect, the energy shift vanishes in the ground state of hydrogen. The energy shift vanishes. It turns out, however, that the shift in the wave function is non-zero. There is a change in the wave function. And it's obvious physically why that should be so. Because if I have my hydrogen atom like this in the absence of an external field, there's a proton in the center with a plus charge, but that's also at the center of a spherically symmetric charge cloud of electrons, which is a minus charge, and those two cancel each other out. So there's no dipole moment there. Now, on the other hand, if I put it in an external field, some electric field like this, let me call it F here, F like this, then what's going to happen is the plus charge, the proton will be pulled one way and the electron cloud will be pulled the other way. And so you get, the electron cloud is supposed to be centered on the negative charge. And so what you get is a shift you get a shift in the electron cloud like this. And you can see that this is going to result in a dipole moment vector going from the negative to the positive charge. This dipole moment vector is what you call an induced dipole moment. It only appears when the external field is applied. I just said many times that the ground state of hydrogen has no permanent electric dipole moment, but it does have an induced electric dipole moment when we apply the electric field, and you can just see from the simple picture why that's so. Now let's try to get the same thing from the quantum mechanics. So we do it this way. Instead of looking at shift in the energy now, this is non-degenerate perturbation theory. We look at shift in the wave function. The exact energy eigenfunction psi would be equal to the ground state, which is 1, 0, 0 in this case, because that's the state we're perturbing, plus the correction term, which in the current notation is this. It's a sum on NLM not equal to 1, 0, 0. And then what we've got is state NLM like this. We have NLM like that. We have the perturbation EFZ. We've got the 1, 0, 0, and we divide this by E1 minus En. Take the formula that from the perturbation notes and just change the notation for this problem. That's what you get. Now, let's ask, does this have an electric dipole moment? We'll just look at the Z component of it, because that's what we're working with here. Let's say sandwich psi around d sub z. Well, at lowest order, coming from the 1, 0, 0, the answer is no. That's the same problem we've just been through. That vanishes because of parity. There's no permanent electric dipole moment. That's what that would be if it were non-zero. So let's go on to next order. You're going to get cross terms between the 1, 0, 0 and this sum. So one of those cross terms, what's it going to be? Well, I can take the E and the F out. And let's see here. Just to be clear about this, this is the same thing as psi sandwiched around to minus EZ psi, because that's the Z component of the dipole moment operator. And so for the psi here, I want to take this psi expression, conjugate it to turn it into bra, sandwich it on the two sides of this EZ. You're going to get 1, 0, 0 terms which vanish. Then you're going to get cross terms. So one of the cross terms is going to be this. There's going to be a factor of minus E from here and a factor of E from there, which I'll take out as a minus E squared. There's a factor of F which comes out. I'll take that out. Then we get this same sum and the same restrictions here, the same type of restrictions on the indices. And then we get a 1, 0, 0 from that turned into a bra. We get a Z here from this minus EZ. Then we get the rest of this NLM here, NLM like that. And then the Z is all that's left of this operator because I took the EF out, 1, 0, 0. And then I get the same denominator here, which is E1 minus EN. All right. Now then, let me clean this up a little bit. E1 minus EN, E1 is the ground state in hydrogen, and the energies are increasing. So E1 minus EN is negative. Let me write this as minus EN minus E1. And having done that, let me change this to a plus sign and that to a plus sign so we can deal with positive quantities now. So let's write this way, is that the average value, expectation value of dz, this is proportional to F. So let's write it as alpha times F, where alpha is equal to, oh, and by the way, I needed to plus complex conjugate this because there's two cross terms. So the alpha then is given by this whole expression stripping off the F part. The complex conjugate turns out is equal to the original term, so I just get a factor of 2. You get 2e squared. We get the sum on NLM is not equal to 1, 0, 0. And then what we get is matrix element 1, 0, 0, Z NLM, and then it's NLM, Z in the middle, and 1, 0, 0 on the right. And it's divided by positive denominator En minus E1. Let me box that because this quantity alpha is important. Alpha, as you see, is proportionality between the induced dipole moment and the applied electric field. This is a Z component only. In a fully three-dimensional problem, this would be generalized to where the average dipole moment is equal to alpha times the F vector as in a vector relation like this. You just have things in the Z direction for the simplified problem. This alpha is called the polarizability. It's the polarizability of the hydrogen atom, which, as you see, we can calculate from quantum mechanics. So the polarizability tells the dipole moment that the atom acquires in the presence of the external field, the induced dipole moment. In electrostatics, we define the polarization vector P as the dipole moment per unit volume. So if I let lowercase n be the number of atoms per unit volume, then the polarization vector is equal to n times alpha. Well, it's equal to n times d. Let me write it out properly. It's equal to n times d. But this is the same thing as n times alpha times F, like this, which is the applied electric field. Well, this is normally written this way as chi sub E times F, where chi sub E is the electric susceptibility. And so what we find is the electric susceptibility is equal to n times alpha, where alpha is computed by quantum mechanics. Now, this is a rather simplified model, and it would only work for very dilute gases. There's a an important correction that's needed at moderate gas densities. It leads you to what's called the Clausius-Mazzotti equation, which you may have studied in 209. In any case, it's discussed in Jackson's book. But in any case, I won't go into that, but this at least gives you an outline which works for dilute gases anyway, that allows you to see how you can calculate an electric susceptibility starting from first principles. By the way, once you get chi, you can find the dielectric constant, and of course that's physically measurable. This is not very realistic for a couple of reasons. One is that you don't normally have a gas of hydrogen atoms because they combine together to form molecules. If you really wanted to know the electric susceptibility calculated from first principles for ordinary hydrogen, you'd need to do it for the molecule and not for the atom. However, for helium, which really is single atoms, an analysis like this would work and would actually give you good answers. All right, so that's part of this lesson. So that's the electric susceptibility then. Now then, I want to return to the. So before I go on, are there any questions about that? Because there's some good physics in this.
So this looks like the second order energy correction to.
Yeah, that's what I'm getting at. That's the next topic.
Oh, okay.
Yep. So the next topic is going to go back where I started from, which is to say, let's go back to the ground state and compute the second order energy shift, which if we just use the standard formulas from second order non-degenerate perturbation theory, you end up with this sum. And I think you can see that this is very similar to the sum that we had earlier. It's very similar to the sum that appears here in the polarizability. In fact, let me get some clean paper here and we'll work on that. So if I take the expression for the second order energy shift coming from perturbation theory, I'll change the sign on the denominator, which will bring out an overall minus sign. There's a factor of E and F in the two terms, so you're going to get an E squared F squared. If you put the pieces together, what you find is that delta E second order due to the ground state is equal to -1/2 alpha times F squared. And this alpha is the same alpha that occurred in the polarization. That's to say, where we had D, the average value of D was equal to alpha times F. This is really a vector relation here. Okay. Polarizability occurs also in this formula. You know, the energy of an electric dipole in an external field is the average dipole moment dotted into the external field with a minus sign. That's the orientation of the dipole. If I use that with this induced dipole moment here, dot this into the electric field, I'd get minus alpha times F squared, not -1/2 alpha times F squared. So why do I get the 1/2 for the energy shift? The reason is that this is not a permanent electric dipole moment, it's an induced dipole moment. So if you think about bringing the electric field up gradually up from 0 to its final value, as you do so, the D is going to change as the field changes. And so in effect, what you're doing is you're doing an integral to compute the total energy that was needed to achieve the final configuration. That's where the factor of 1/2 came from, and integrating FDF basically. All right, in any case, this is the second order energy shift. All right, so this is called the quadratic Stark effect then, is the second order energy shift. Now, I have about 5 minutes left, and I'm going to try to do one last thing, which is to create at least an estimate for the polarizability. Let's go back to it here. Let me put it in a place where I can lay it on a piece of paper here. There's the formula for the polarizability. Let me show you some tricks here we can use to at least estimate this polarizability. We'll get a bound on it. So it's going to work like this. You'll see the tricks. The energy levels are an increasing function of n, so En is greater than E1. In fact, En is greater than or equal to E2. Let me do it that way. En is greater, because the N here is N is not equal to 1, so N starts with 2. So En is greater than or equal to E2. That means that En minus E1 is greater than or equal to E2 minus E1. Or if I take the reciprocal, 1 over En minus E1 is less than or equal to 1 over E2 minus E1. Why am I doing this? Because we have this denominator here in this sum, and it depends on N. That's what makes this sum hard to do, is that denominator. But by using an inequality, I'm going to replace the denominator by a constant that's independent of N, and then we can take it out of the sum. So that's the strategy. Well, let's look at E2 minus E1. E2 is minus 1 over 8 times E squared over A naught. And E1 is minus 1/2 E squared over A naught. And combining those together, we get 3/8 of E squared over A naught. So if I put this in here, what I get is that alpha then is less than or equal to, it's now an inequality of 2E squared. I need to divide by this, that becomes 8/3. This wasn't the denominator, so I'm taking it out of the sum because it's constant now and turning it upside down because I'm dividing. A naught divided by E squared. And now I get the sum on NLM, same sum, restricted not to be not equal to 100. And then what we get is 100 Z NLM 100. I'm sorry, Z in the middle, and then 100 on the right hand side, and the denominator is now gone. And so this thing can be cleaned up. The E squareds cancel. We get 16/3 A naught, like that. And as far as this sum is concerned, now that I've got the denominator out of there, the denominator vanished when En was equal to E1, but since I've removed it, I don't have to worry about that. And I can actually include the 100 term again. In fact, the 100 term is 0 because of parity. So including it doesn't change the value. So I can just take this restriction out and think of summing over all NLM. And if we do that, you see you have a resolution of the identity here. So what you end up is 100 sandwiched around now the operator Z squared 100. And this is not 16 over A naught. Here, this coefficient is 16/3 times A naught. Goes in there. This matrix element, it turns out, is A00 squared. So what we get is 16/3 A naught cubed. And so we end up with an inequality. Alpha is less than or equal to 16/3 A naught cubed. Okay. It turns out there's an exact analysis that allows one to evaluate the susceptibility exactly. I think this is carried out by Del Garno at Harvard. And the alpha is equal to, in fact, 9 halves, if I've got it right, A naught cubed. 16/3 is 5 and a third, and 9 halves is 4 1/2. So this estimate that we used worked pretty well. I mean, it worked. I mean, we had an upper bound, and it wasn't too far off from actually the exact answer. Anyway, this is a trick that can be used here to compute the exact answers. This really is the polarizability of the ground state of hydrogen. Okay, are there any questions about that?
So earlier when we were making the comparison with the classical case where we had like d dot f or negative d dot f is the energy, and then like for a first order we said that it should be that the energy shift should be 0, kind of like in the classical case. And
well, no, in the classical case, if you have a dipole, then the minus d dot f minus d dot f is the energy of orientation of that dipole in the external field.
Right, right. So then
What
for
we're finding in the quantum problem is that it's really hard to come up with a permanent electric dipole moment.
right, right. So then I guess what we were saying was that the expectation of the dipole is 0 for
For most
uh,
of the states we looked at, yeah.
yeah. So then, but then if we do second order perturbation theory like what we just did,
Yes,
we do get an energy shift.
you do, but it's second order and it's much smaller than you would have had by first order. And it's the induced dipole moment you're seeing now, not the permanent dipole moment. I mean, the comparison between the two depends on how strong the electric field is. Because if you make the field strong enough, then the quadratic term becomes comparable to the linear term. But those are extraordinarily strong electric fields. That's where the applied electric field becomes comparable to the nuclear electric field.
Okay.
Yeah.
So if we want to think of this classically, then we can think of like the cloud sort of moving to one side.
Yes, that's exactly what happens. The cloud moves to one side. That's the induced dipole moment.
All right.
Now, in chemistry courses, they frequently talk about polar molecules like hydrogen chloride, and they say it has a permanent electric dipole moment. So there's a question of, and then that is oriented in the external field by just like a classical dipole with the same energy. It's basically minus P dot E. I'm calling it D dot F here, but it's minus P dot E is a normal notation for it. So there's a question then about why hydrogen chloride has a permanent electric dipole moment, and all these other cases I've been telling you about don't. And that's an interesting subject, which unfortunately I don't have time to go into now. But it has to do with the strength of the electric field. Is to say that you only see this supposed permanent electric dipole moment if the electric field is strong enough. I may give a homework problem on that. You can see it for yourself how it works out. No, I won't. It's too the hydrogen chloride is too complicated. There's other examples where one can work it out, though. Are there any other questions about this? So the Stark effect is a simple exercise in perturbation theory, but it's also a massive lesson in symmetries and how important a role symmetry plays in the analysis of a problem like this. I hope you can see that. All right, well, that's all for tonight then, if there's no more questions. And we'll start on fine structure effects in the next lecture. Let me stop the screen share. And now I'll stop recording.